Picture this. You're an astronaut floating in the infinite darkness of space, your helmet visor reflecting the light of 1,000 distant suns. You've just discovered a world where diamonds rain from ruby skies, where glass shards slice through the atmosphere at 5,000 miles per hour, where ancient planets, older than time itself, dance around the corpses of dead stars. This isn't science fiction. This isn't some fever dream conjured by Hollywood writers desperate for the next blockbuster. These worlds exist right now, scattered across our galaxy like cosmic aberrations that shouldn't be possible according to everything we thought we knew about planetary physics. Tonight, we're embarking on a journey to the 10 strangest planets in the universe. Worlds so bizarre, so utterly alien, that they're forcing scientists to rewrite the fundamental laws of planetary formation. Before we dive in, I'd love to know where you're watching from and which impossible world you think sounds the most terrifying. And if you're as fascinated by these cosmic mysteries as I am, hit that like button and subscribe to join our community of interstellar explorers. Get ready. The journey begins now. Here's what should absolutely terrify you about the cosmos we inhabit. Every single planet we're about to explore exists within a few hundred light years of Earth. That means, in the grand scale of our galaxy, these impossible worlds are practically next-door neighbours. And if planets this strange exist so close to home, imagine what nightmarish creations are lurking in the deepest reaches of space, waiting to be discovered by our telescopes. But here's the thing that keeps astronomers awake at night, staring at data that shouldn't exist. Each of these worlds represents a fundamental violation of what we believed possible. They're not just unusual, they're actively defying the laws of physics as we understand them, forcing us to confront the uncomfortable truth that our models of planetary formation might be embarrassingly incomplete. By the time we're finished tonight, you'll understand why the universe is far stranger and more dangerous than anyone dared imagine just a few decades ago. You'll see how these cosmic oddities are rewriting textbooks and challenging our most basic assumptions about what kinds of worlds can exist in the darkness between stars. Chapter 1. HD 1897-33b. The Glass Rain Hell. Let me introduce you to your first nightmare. HD 1897-33b sits roughly 63 light-years from Earth, and from a distance, it looks absolutely beautiful. This cobalt blue gem appears almost identical to Earth in photographs, with that same stunning azure hue that makes our home planet so distinctive from space. But here's where the beauty ends, and the horror begins. That gorgeous blue colour isn't from oceans or atmosphere like Earth's. It's from tiny particles of silicate glass suspended throughout the planet's atmosphere, each fragment heated to over 2,400 degrees Fahrenheit. Imagine standing on the surface of this world if you could somehow survive the crushing atmosphere and temperatures that would instantly vaporize steel. The sky above you would shimmer with an ethereal blue beauty that poets might weep to describe. But that beauty would be the last thing you'd ever see, because those glass particles aren't just floating peacefully in the air. Winds on HD 1897-33 blow at speeds exceeding 5,000 miles per hour. That's 7 times faster than the speed of sound on Earth. These hypersonic winds catch those superheated glass fragments and turn them into projectiles moving at velocities that would make bullets seem sluggish by comparison. The planet experiences perpetual glass rain, but not the gentle precipitation you might imagine. We're talking about microscopic razors falling sideways at incomprehensible speeds, slicing through the atmosphere in storms that would make the most violent Earth hurricane look like a gentle spring breeze. What baffles scientists is how this glass forms and maintains its structure under such extreme conditions. The silicate particles should theoretically break apart or melt completely at these temperatures and wind speeds. Yet somehow they persist, creating a stable atmospheric phenomenon that shouldn't be possible according to our understanding of materials science. Dr. Frederick Pont from the University of Exeter, who led the team that discovered these properties, admits that the mechanisms behind this glass rain formation remain completely mysterious. The planet is challenging fundamental assumptions about atmospheric chemistry and particle dynamics in ways that are forcing researchers to develop entirely new theoretical frameworks. But HD 1897-33b has another secret that makes it even more terrifying. The planet is tidally locked to its star, meaning one side faces perpetual daylight, while the other remains in eternal darkness. The temperature differential between these two sides creates atmospheric pressure gradients so extreme they generate those impossible wind speeds we discussed. On the day side, temperatures soar above 2000 degrees Fahrenheit, hot enough to melt copper. The night side, while still scorching by Earth standards, is relatively cooler at around 1000 degrees. This temperature difference drives massive atmospheric circulation patterns that transport the glass particles from the day side to the night side and back again in endless, violent cycles. Recent observations using the Spitzer Space Telescope have revealed that the planet's atmospheric dynamics are even more complex than initially thought. The glass particles appear to be constantly forming, dissolving, and reforming as they cycle through different temperature zones, creating a kind of atmospheric recycling system that operates on principles we don't fully understand. The planet's extreme proximity to its host star also subjects it to intense stellar radiation that ionizes gases in its upper atmosphere, creating a thin envelope of plasma that glows faintly in ultraviolet light. This ionosphere interacts with the planet's magnetic field, if it possesses one, to create complex electromagnetic phenomena that could theoretically be detectable from interstellar distances. Computer models suggest that HD 1897-33b's glass rain might create unique optical effects as the planet transits in front of its host star. The suspended silicate particles could scatter starlight in ways that create subtle spectroscopic signatures, allowing astronomers to study the composition and behavior of this impossible atmospheric phenomenon from dozens of light years away. The study of HD 1897-33b has revolutionized our understanding of atmospheric chemistry on hot Jupiter planets. It's shown that worlds orbiting close to their stars can develop weather systems operating according to principles that have no terrestrial analogues, challenging our assumptions about how atmospheric circulation patterns develop and persist under extreme stellar heating. Recent theoretical work suggests that glass rain might be more common than initially thought, occurring on multiple hot Jupiter planets throughout the galaxy. If this proves true, it would mean that one of the universe's most beautiful and deadly atmospheric phenomena might be occurring simultaneously on thousands of worlds scattered throughout our local region of space. The discovery has also raised questions about how planets with such violent atmospheric conditions could ever be detected by traditional methods. The glass storms might interfere with spectroscopic measurements in ways that could cause astronomers to overlook similar worlds, suggesting that our galaxy might harbour many more glass rain hells than current surveys have revealed. Chapter 2. 55 Cancri, the Diamond World, worth more than Earth's economy. Now let me tell you about a world that would make the greediest treasure hunters weep with both desire and despair. 55 Cancri A, located 41 light-years from Earth, is quite possibly the most valuable object in the known universe from a purely monetary perspective. This super-Earth, twice the diameter of our planet and 8 times more massive, orbits so close to its star that a complete year lasts just 18 Earth hours. But what makes this world legendary isn't its rapid orbit or extreme proximity to its stellar furnace. It's what scientists believe this planet might be made of. Based on spectroscopic analysis and theoretical modelling of the planet's formation, Researchers estimate that roughly 1/3 of 55 Cancri's mass consists of pure carbon, and under the crushing pressures and searing temperatures in the planet's interior, much of that carbon exists in crystalline form. We're talking about diamond, lots and lots of diamond. To put this in perspective, if we could somehow mine this world and transport its resources back to Earth, the diamond content alone would be worth approximately $26.9 nonillion. That's a number so large it's almost meaningless in human terms, but it represents roughly 384 quadrillion times more wealth than Earth's entire gross domestic product. But here's where the story becomes even more fascinating and bizarre. Recent observations using the James Webb Space Telescope have revealed that 55 Cancri e has somehow managed to regenerate its atmosphere after its star completely stripped away its original atmospheric envelope. Think about what this means. The planet experienced atmospheric loss so complete that it should have been left as a bare, airless rock. Yet somehow, it's managed to develop a secondary atmosphere composed of what appears to be carbon monoxide, carbon dioxide, and other volatile compounds. The surface temperatures on 55 Cancri A reach nearly 4,000 degrees Fahrenheit on the day side, hot enough to melt most metals. Under these conditions, the planet's surface is likely covered by a global ocean of molten lava with diamond formations embedded throughout the planet's structure, like jewels in a cosmic crown. Dr. Renyu Hu from NASA's Jet Propulsion Laboratory, who led the atmospheric studies, describes the situation as unprecedented in exoplanet science. The planet shouldn't be able to maintain any kind of atmosphere under such extreme stellar bombardment. Yet observations clearly show atmospheric absorption features that indicate the presence of substantial gaseous envelopes. The mechanism behind this atmospheric regeneration remains completely unknown. Some theories suggest that volcanic outgassing from the planet's molten interior continuously replenishes the atmosphere faster than stellar winds can strip it away. Others propose that the planet's strong magnetic field, generated by its molten core, provides sufficient protection to allow atmospheric retention. But there's another mystery that has scientists completely stumped. The planet's density doesn't quite match what we'd expect from a world composed primarily of carbon and iron. Some researchers now question whether the diamond planet hypothesis is entirely accurate, suggesting that the world's composition might be even more exotic than initially believed. Recent analysis of the host star's chemical composition has revealed that it contains more oxygen relative to carbon than previously thought, which could indicate that 55 Cancri e formed through processes we don't yet understand. The planet might represent an entirely new category of super-Earth that challenges our models of how rocky planets form and evolve. The discovery of atmospheric regeneration on 55 Cancri A has profound implications for our understanding of planetary habitability around other stars. If worlds can recover from complete atmospheric loss and develop secondary atmospheres, it dramatically expands the range of conditions under which planets might maintain gaseous envelopes capable of supporting complex chemistry. Theoretical models suggest that 55 Cancri A's diamond-rich interior could create unique geological processes that have no analogues in our solar system. The extreme pressures required to maintain crystalline carbon at planetary scales could drive forms of internal convection that generate unusually strong magnetic fields and enhanced volcanic activity. The planet's rapid 18-hour orbit also subjects it to extreme tidal heating that could contribute to its geological activity. The gravitational forces from its nearby star continuously flex and deform the planet's interior, potentially maintaining molten regions throughout its structure, despite billions of years of evolution. Computer simulations attempting to model 55 Cancri's formation consistently struggle to reproduce its observed properties using standard planetary accretion theories. The planet appears to have assembled itself through processes that operated under conditions significantly different from those that created the worlds in our solar system. The ongoing study of 55 Cancri E is providing unprecedented insights into how super-Earth planets evolve around Sun-like stars. It's revealing that these worlds can experience complex atmospheric and geological evolution that creates planetary environments completely unlike anything we see among the terrestrial planets in our own cosmic neighborhood. Chapter 3. WASP-76b, the Iron Rain, Inferno. If you thought glass rain was terrifying, let me introduce you to a world where the precipitation consists of molten iron droplets falling from clouds of vaporized metal. WASP-76b, located 640 light-years from Earth, represents atmospheric chemistry gone completely insane. This ultra-hot Jupiter completes one orbit around its star every 1.8 Earth days, locked in such a tight gravitational embrace that the planet's day side reaches temperatures exceeding 4,300 degrees Fahrenheit. That's hot enough to vaporize iron, titanium, and virtually every other metal in the periodic table. But here's where the physics becomes truly nightmarish. The planet is tidally locked, so while the day side roasts under constant stellar bombardment, the night side remains relatively cooler at around 2,700 degrees Fahrenheit. This temperature differential creates some of the most extreme weather patterns ever discovered. Atmospheric circulation models show that supersonic winds, blowing at speeds exceeding 8,000 miles per hour, transport vaporized metals from the scorching day side to the cooler night side. As these metal vapors encounter the lower temperatures, they condense into liquid droplets and fall as metallic rain. Imagine clouds composed entirely of iron vapor, glowing white-hot against an alien sky. As these clouds drift toward the night side, they cool and darken, transforming into storms that rain liquid iron onto the planet's surface. The droplets fall through an atmosphere so dense and turbulent that they're constantly accelerated and decelerated by competing wind currents. Dr. David Ehrenreich from the University of Geneva, who led the team that discovered these iron rain patterns, describes the phenomenon as the most extreme weather system we've ever detected on an exoplanet. The spectroscopic signatures clearly show iron absorption lines appearing and disappearing as the planet rotates, providing direct evidence of this metallic precipitation cycle. But WASP-76b has revealed another atmospheric mystery that has scientists completely baffled. The planet appears to be losing its atmosphere at an accelerated rate, with material streaming away into space in long comet-like tails. Yet somehow, despite this ongoing atmospheric loss, the iron rain patterns remain stable and consistent. This suggests that the planet's interior is continuously replenishing its atmosphere through volcanic outgassing or other geological processes. The world might be caught in a constant battle between atmospheric loss and atmospheric renewal, creating a dynamic equilibrium that maintains its exotic weather patterns. Recent observations have also revealed that WASP-76b's magnetic field is far stronger than theoretical models predict. This powerful magnetosphere might be responsible for channeling some of the metallic atmospheric components into specific circulation patterns, creating the organized iron rain systems that we observe. The planet's extreme proximity to its star means that it's also experiencing intense tidal heating, which could be driving geological activity in the planet's core. This internal heat source might explain how the world maintains its atmospheric composition despite the constant stellar bombardment that should strip away its gaseous envelope. Spectroscopic analysis has revealed that WASP-76b's dayside atmosphere contains not just vaporized iron, but also gaseous forms of titanium, vanadium, and other refractory metals that normally exist only in solid form. The extreme temperatures create a kind of metallic soup where elements that would be locked in mineral structures on cooler worlds float freely through the atmosphere. The planet's iron rain represents more than just an exotic weather phenomenon. It's evidence of atmospheric chemistry, operating under conditions so extreme that they create entirely new categories of planetary meteorology. Traditional concepts of precipitation, cloud formation, and atmospheric circulation become inadequate when dealing with weather systems composed of vaporized metals. Computer models suggest that WASP-76b's metallic weather patterns might create feedback loops that influence the planet's overall atmospheric dynamics. Regions where iron rain falls most heavily could develop different surface compositions that affect local heating rates, potentially creating persistent weather patterns that endure for geological periods. The discovery of iron rain on WASP-76b has forced atmospheric scientists to expand their theoretical frameworks to include precipitation cycles composed of materials that exist only in extreme stellar environments. It's revealed that the universe's capacity for creating exotic weather systems extends far beyond anything we encounter in our temperate solar system. Recent theoretical work suggests that metallic precipitation might be common on ultra-hot Jupiter planets throughout the galaxy. If confirmed, this would mean that worlds experiencing iron rain, titanium snow, and other forms of metallic weather might number in the thousands among the exoplanets discovered so far. Chapter 4. Strangest, the planet darker than coal. In the cosmic catalogue of impossible worlds, Strangest stands out as perhaps the most visually striking anomaly ever discovered. This Jupiter-sized planet, located 750 light-years from Earth, reflects less than 1% of the light that reaches it, making it literally darker than coal, black acrylic paint, or any other substance we've encountered on Earth. To understand just how extraordinary this is, consider that even the darkest materials on our planet reflect at least some visible light. Vantablack, one of the darkest artificial substances ever created, still reflects about 0.035% of incident light. Strangest reflects less than 0.1%, making it darker than anything in our terrestrial experience. The planet orbits its star at a distance of only 3 million miles, completing one revolution every 2.5 days. At this proximity, the world receives intense stellar radiation that heats its atmosphere to over 3,000 degrees Fahrenheit. Yet despite absorbing virtually all incoming light, the planet emits only a faint red glow, like the dying embers of a cosmic fire. Dr. David Kipping from Columbia University, who led the team that discovered Strangest extraordinary darkness, admits that current atmospheric models cannot explain this extreme light absorption. It's not clear what is responsible for making this planet so extraordinarily dark, he states. The physics just doesn't add up according to our understanding of atmospheric chemistry. Theoretical models suggest that hot Jupiter planets should reflect somewhere between 10 and 40% of incident starlight, depending on their atmospheric composition and cloud cover. Strangest near-perfect light absorption represents a completely unprecedented phenomenon that challenges our understanding of how planetary atmospheres interact with stellar radiation. One hypothesis suggests that the planet's atmosphere contains exotic light-absorbing compounds like vaporized sodium, potassium, or gaseous titanium oxide. These materials could theoretically absorb visible light across broad spectral ranges, but even the most optimistic models cannot account for the near-total absorption that observations reveal. Another possibility is that the planet's extreme temperature and pressure conditions have created atmospheric chemistry that we've never encountered before. The combination of intense stellar radiation and rapid atmospheric circulation might be generating molecular compounds that don't exist under any conditions we can replicate in terrestrial laboratories. The discovery of Strangest's darkness was only possible because of the unprecedented precision of the Kepler Space Telescope. The brightness variations caused by the planet's orbit are incredibly subtle, changing by only 6.5 parts per million relative to the host star's brightness. This represents the smallest photometric signal ever detected from an exoplanet at the time of discovery. But Tatooine holds another secret that makes it even more mysterious. Despite its extreme darkness, the planet shows evidence of atmospheric variability that suggests complex weather patterns and circulation systems. The subtle changes in its thermal emission indicate that different regions of the atmosphere have different temperatures and compositions. Recent analysis suggests that TRES-2b might be experiencing some form of atmospheric instability that creates temporary bright regions before they are absorbed back into the planet's overall darkness. These transient features could provide clues about the exotic atmospheric chemistry that makes this world so uniquely light-absorbing. The implications of TRES-2b's existence extend far beyond a single bizarre planet. If atmospheric conditions can create such extreme light absorption, it suggests that there might be entire categories of dark worlds that remain undetected in our galaxy simply because they're too black to observe with current technology. Spectroscopic observations have revealed that TRES-2b's atmosphere contains unusual concentrations of alkali metals and other light-absorbing compounds. But the specific mechanisms that create such efficient absorption remain mysterious. The planet might be experiencing atmospheric chemistry that operates according to principles we haven't discovered yet. Computer simulations attempting to reproduce TRES-2b's optical properties consistently fail when using standard atmospheric chemistry models. The planet appears to require exotic molecular processes or previously unknown forms of matter interaction to explain its observed darkness. The planet's rapid orbit and extreme stellar heating create atmospheric dynamics that might contribute to its light-absorbing properties. High-altitude winds exceeding several thousand miles per hour could transport light-absorbing compounds throughout the atmosphere in ways that maximize their optical efficiency. As our telescopes become more sensitive and our detection methods more sophisticated, we might discover that dark planets like TRES-2b are far more common than we currently realize. The universe could be filled with shadowy worlds that absorb light so efficiently they're practically invisible against the cosmic background. Recent theoretical work suggests that TRES-2b's extreme darkness might be related to its atmospheric pressure profile, with light-absorbing compounds concentrated at specific altitude layers where they can maximize their interaction with incoming stellar radiation. This could create a kind of atmospheric architecture specifically optimized for light absorption. Chapter 5. PSR B16 20-26b. The Ancient Wanderer That Shouldn't Exist. Deep in the heart of the globular cluster, M4, floating in a region of space so old it predates the formation of our solar system by billions of years, exists a world that has fundamentally shattered our understanding of planetary formation. PSR B1620-26b, nicknamed Methuselah by astronomers, is approximately 12.7 billion years old, making it nearly 3 times the age of Earth and almost as old as the universe itself. This ancient giant, with a mass 2.5 times that of Jupiter, orbits not one star but 2 stellar corpses locked in a gravitational dance of death. Its primary companion is a pulsar, the rapidly spinning remnant of a massive star that exploded in a supernova billions of years ago. The secondary companion is a white dwarf, the dense core of another star that exhausted its nuclear fuel and collapsed into a city-sized object with the mass of our Sun. Here's what should absolutely blow your mind about this cosmic senior citizen. When Methuselah first formed, the universe was barely 1 billion years old. There were no heavy elements like carbon, oxygen, or silicon available in significant quantities. The first generation of stars had only just begun forging these essential building blocks of rocky planets in their nuclear furnaces. According to everything we thought we knew about planetary formation, worlds like Methuselah simply couldn't exist. Planets require heavy elements to form solid cores that can gravitationally capture gas and dust from their surrounding environment. But this ancient world somehow assembled itself from a cosmic soup that was almost entirely hydrogen and helium. Dr. Stein Sigurdsson from Penn State University, who was part of the team that discovered this impossible planet, describes it as a cosmic time traveler that's forcing us to completely reconsider when and how planets can form. The very existence of Methuselah suggests that planetary formation began much earlier in cosmic history than we ever imagined possible. But the mystery deepens when you consider the violent environment this planet has survived. Pulsar companions experience radiation bombardment so intense it would sterilize any known form of life within minutes. The pulsar spins 30 times per second, sweeping beams of deadly radiation across space, like a cosmic lighthouse gone mad. Methuselah orbits this stellar graveyard at a distance roughly equivalent to Uranus's orbit around our Sun, completing one revolution every 100 Earth years. For over 12 billion years, this world has endured radiation levels that would vaporize Earth's atmosphere in seconds, yet somehow it has maintained its structural integrity and orbital stability. Recent computer models suggest that Methuselah might have originally formed around a normal star, then been gravitationally captured when that star's companion went supernova. This capture process should have either destroyed the planet entirely or flung it into interstellar space. Yet somehow, Methuselah not only survived, but settled into a stable, three-body orbital configuration. The planet's survival through multiple stellar death events represents a cosmic endurance test that challenges our understanding of planetary resilience. It's witnessed the birth and death of countless stars, survived supernova explosions that would have obliterated most worlds, and continues to orbit peacefully in one of the most hostile environments imaginable. What makes Methuselah even more extraordinary is what its existence implies about planetary abundance throughout the universe. If planets could form in the early universe using only primordial hydrogen and helium, there might be billions of ancient worlds scattered throughout our galaxy, many of them predating Earth by enormous time spans. These primordial planets might represent an entirely unknown category of world that formed through mechanisms we haven't discovered yet. They could provide insights into the very earliest epochs of cosmic history, serving as time capsules that preserve information about conditions in the infant universe. The gravitational dynamics of the PSRB 1620-26 system create a complex orbital environment where Methuselah experiences constant perturbations from both its stellar companions. Computer simulations show that the planet's orbit precesses slowly over time, cycling through different configurations that expose it to varying levels of radiation from the pulsar. Recent theoretical work suggests that Methuselah's composition might be fundamentally different from planets that formed later in cosmic history when heavy elements were more abundant. The world could contain exotic forms of matter that assembled under the unique conditions present in the early universe. The study of ancient planets like Methuselah is revolutionizing our understanding of how planetary systems evolve over cosmic timescales. It's revealing that worlds can survive through multiple generations of stellar evolution, adapting to changing conditions that would destroy less resilient planetary systems. The discovery has profound implications for astrobiology, suggesting that habitable conditions might have existed on planets billions of years before Earth formed. If life could have emerged on ancient worlds like Methuselah, it would mean that biological evolution has had far more time to develop complex forms than we previously thought possible. Chapter 6. Kepler 16b, the real-life Tatooine with twin sunsets. Science fiction writers have long imagined worlds orbiting binary star systems, but Kepler 16b proves that reality is far more spectacular and terrifying than any Hollywood imagination. This Saturn-sized world, located 200 light-years from Earth, orbits not one star, but two, creating a celestial dance of impossible complexity and beauty. Picture yourself standing on the frozen surface of this world, watching as two suns trace separate paths across an alien sky. One star, slightly smaller than our sun, glows with a warm yellow light. Its companion, a red dwarf barely 1/3 the mass of our sun, casts the landscape in an eerie crimson glow. As both stars set on opposite horizons, the sky erupts in colours that no human eye has ever witnessed. But this binary sunset spectacle conceals gravitational chaos that makes Kepler-16b one of the most dynamically unstable worlds ever discovered. The planet's orbit precesses like a wobbling top, constantly shifting orientation as the gravitational influences of both stars tug at its trajectory in competing directions. Dr. Lawrence Doyle from the SETI Institute, who led the discovery team, describes Kepler-16b as a world caught in an eternal gravitational wrestling match. The planet's orbital period varies unpredictably as it moves through regions of stronger and weaker gravitational influence, sometimes completing a revolution in 229 days, sometimes taking longer as the binary star's own orbital mechanics interfere with its path. What makes this world particularly nightmarish is its surface temperature, which averages -100 degrees Fahrenheit. Despite receiving light from two stars, the combined stellar output is insufficient to warm the planet's atmosphere. Kepler-16b exists in a perpetual ice age, where any liquid water would freeze solid within minutes. The atmospheric dynamics on this world are unlike anything else we've encountered. Computer models suggest that the dual stellar heating creates complex circulation patterns, where different hemispheres experience radically different weather systems depending on which star is providing primary illumination at any given time. The planet's elliptical orbit means it experiences dramatic seasonal variations as it moves closer to and farther from the binary star system. During closest approach, surface temperatures might rise enough to sublimate frozen gases, creating temporary atmospheres that collapse back into ice as the planet swings away into the outer regions of its orbit. But here's what truly baffles scientists about Kepler-16b. It shouldn't exist at all. Theoretical models of planetary formation in binary star systems suggest that gravitational perturbations should prevent stable planet formation in the orbital zone where Kepler-16b resides. The competing gravitational influences should have either prevented the planet from forming or ejected it from the system entirely. Recent observations have revealed that Kepler-16b's orbit is slowly decaying, spiraling inward toward the binary stars at a rate of about 1 meter per year. This orbital decay suggests that the planet might be doomed to eventual destruction as it's torn apart by tidal forces or consumed by one of its parent stars. The discovery of Kepler-16b has forced astronomers to completely revise their understanding of where planets can form and survive in multiple star systems. It represents proof that gravitational chaos doesn't necessarily prevent planetary formation, opening up vast new regions of space where we might discover other circumbinary worlds. Theoretical calculations suggest there could be millions of binary star systems in our galaxy capable of hosting planets, like Kepler-16b. If even a small percentage of these systems contain worlds, it would dramatically increase estimates of planetary abundance throughout the Milky Way. The planet's complex orbital dynamics create unique tidal effects that could drive geological activity in ways that have no analogues in single-star planetary systems. The competing gravitational influences from two stars could generate internal heating through tidal flexing that maintains geological activity for billions of years. Spectroscopic observations have revealed that Kepler-16b possesses a substantial atmosphere composed primarily of hydrogen and helium, with trace amounts of water vapor and other volatiles. The atmospheric composition suggests that the planet formed in the cooler outer regions of the binary system before migrating to its current orbit. The dual stellar illumination creates atmospheric heating patterns that generate complex weather systems, unlike anything seen on planets orbiting single stars. Different regions of the atmosphere experience heating from different stellar sources at different times, creating circulation patterns that constantly shift and evolve. Recent computer simulations have shown that planets in circumbinary orbits, like Kepler-16b, experience long-term orbital instability that could eventually lead to ejection from their host systems. The planet might represent a temporary phase in the evolution of binary star systems, suggesting that many such worlds might eventually become rogue planets wandering through interstellar space. Chapter 7. WASP-12b, the doomed world, being devoured alive. In the cosmic catalogue of planetary horror stories, few worlds face a fate more gruesome than WASP-12b. This bloated gas giant, located 870 light-years from Earth, is being slowly cannibalized by its own star in a process so violent it's visible from interstellar distances. WASP-12b orbits its host star at a distance of only 2 million miles, so close that it completes one revolution in just 26 hours. At this proximity, the planet experiences tidal forces so extreme they've stretched it into an egg shape, with its near side bulging toward the star like a cosmic teardrop frozen in the moment before impact. The star's intense gravity is literally ripping away the planet's atmosphere, creating a stream of hot gas that flows from the planet to the star in a process called Roche lobe overflow. Material from WASP-12b's outer atmosphere spirals into an accretion disk around the star, glowing white-hot as it's compressed and heated to temperatures exceeding 10,000 degrees Fahrenheit. Dr. Xulin Li from Peking University, who led the research team studying this cosmic cannibalism, estimates that WASP-12b is losing approximately 10 billion tons of material every second. At this rate of mass loss, the planet will be completely consumed within 10 million years, a geological instant in cosmic terms. But the death spiral of WASP-12b reveals atmospheric physics operating under the most extreme conditions imaginable. The planet's day side, locked in perpetual facing toward its stellar tormentor, reaches temperatures approaching 4,000 degrees Fahrenheit. This intense heating causes the planet's atmosphere to expand dramatically, making it easier for the star's gravity to strip away material. Spectroscopic analysis has revealed something absolutely extraordinary about the composition of material being torn from WASP-12b. The stellar atmosphere shows enhanced concentrations of heavy elements like carbon and oxygen that could only have come from the planet's interior. This means the star isn't just consuming the planet's atmosphere, but actually dredging up material from deep within its core. The implications are staggering. We're witnessing a process where a star is literally digesting a planet, incorporating its heavy elements into its own composition. Over millions of years, this stellar cannibalism could significantly alter the host star's chemical makeup, creating a stellar signature that bears the fingerprints of the consumed world. Recent observations using the Hubble Space Telescope have revealed that the material streaming from WASP-12b extends far beyond the planet's immediate vicinity. The hot gas forms a vast comet-like tail stretching millions of miles behind the planet's orbit, creating a luminous trail that's visible in ultraviolet wavelengths. This tail material eventually falls onto the star's surface, releasing enormous amounts of energy that can be detected as excess emission in the star's spectrum. The process creates a feedback loop where the star's enhanced luminosity from consuming planetary material accelerates the rate at which it can strip away more atmospheric mass. But WASP-12b holds another secret that makes its fate even more tragic. Analysis of the planet's bulk composition suggests it formed much farther from its star, in the cooler outer regions of the solar system, where gas giants typically assemble. Gravitational interactions with other planets or stellar companions gradually pushed WASP-12b inward over millions of years until it reached its current death spiral orbit. This inward migration process, called planetary migration, appears to be relatively common in exoplanetary systems. It suggests that many hot Jupiter planets, like WASP-12b, are cosmic refugees, displaced from their original orbits and condemned to eventual destruction by their host stars. The study of WASP-12b is providing unprecedented insights into the final stages of planetary evolution. It's showing us what happens when worlds venture too close to their stars, revealing the ultimate fate that awaits any planet that finds itself trapped in such an intimate gravitational embrace. Computer models suggest that as WASP-12b continues its death spiral, the rate of mass loss will accelerate exponentially as the planet moves closer to its star. The final phases of consumption could occur rapidly, with the planet being completely devoured within just a few thousand years. Once it reaches a critical distance, the planet's magnetic field, if it still possesses one, is being constantly stripped away along with its atmosphere, leaving the world increasingly vulnerable to stellar wind erosion. The loss of magnetic protection accelerates atmospheric loss and exposes the planet's interior to direct stellar bombardment. Recent theoretical work suggests that WASP-12b's consumption might create detectable signatures in the host star's spectrum that could persist for millions of years after the planet is gone. These chemical fingerprints could provide evidence of planetary destruction long after the original world has vanished completely. Chapter 8: Gliese 581g, the phantom world that might not exist. In September 2010, astronomers announced the discovery of what they called the most Earth-like planet ever found. Gliese 581g, orbiting a red dwarf star just 20 light-years from Earth, appeared to sit perfectly within the habitable zone where liquid water could exist on its surface. For a brief, shining moment, humanity thought we'd found our first potentially habitable neighbour. Then the planet vanished. Not literally, of course, but as more precise observations accumulated, the evidence for Gliese 581g's existence began to crumble. Some research teams confirmed its presence, while others found no trace of it in their data. The planet became a cosmic phantom, appearing and disappearing depending on which instruments were used and how the data was analysed. Dr. Stephen Vogt from UC Santa Cruz, who led the original discovery team, remains convinced that Gliese 581g exists. His analysis of radial velocity measurements shows clear evidence of gravitational perturbations that could only be caused by a planet with roughly 3 times Earth's mass orbiting every 37 days. But other research groups, using the same observational data, have reached completely opposite conclusions. Dr. Michael Mayer from the Geneva Observatory, whose team operates one of the most precise planet hunting instruments in the world, states flatly that there is no planet G in the Gliese 581 system. This scientific controversy reveals just how close we are to the limits of current planet detection technology. The gravitational influence of Gliese 581g, if it exists, is so subtle that it approaches the noise level of our most sensitive instruments. We're trying to detect the cosmic equivalent of a whisper in a hurricane. The Gliese 581 system itself is a fascinating laboratory for studying planetary formation around low-mass stars. The red dwarf host star has only 1/3 the mass of our Sun and emits most of its energy in infrared wavelengths. Any planet in the habitable zone would be tidally locked, with one side permanently facing the star while the other remains in eternal darkness. If Gliese 581g does exist, its surface conditions would be unlike anything in our solar system. The day side might have temperatures suitable for liquid water, while the night side could be frozen solid with carbon dioxide snow. Between these extremes, there might be a narrow twilight zone where conditions could theoretically support some form of life. But even if the planet exists, Recent studies suggest its atmosphere would be far more complex and potentially hostile than initially thought. Computer models indicate that tidal locking around red dwarf stars creates atmospheric circulation patterns that could transport heat from the day side to the night side, but might also generate supersonic winds and violent weather systems. The controversy over Gliese 581g highlights a fundamental challenge in exoplanet science. We're using indirect methods to detect worlds so distant that their light takes decades to reach us. Every measurement is filtered through layers of atmospheric interference, instrumental noise, and statistical uncertainty. The phantom planet has become a cautionary tale about the dangers of premature announcements in exoplanet research. The initial discovery generated enormous public excitement and media coverage, only to dissolve into scientific uncertainty and confusion. It's taught astronomers to be more conservative about claiming discoveries that push the boundaries of observational capability. Yet the search for Gliese 581g continues. New instruments with unprecedented precision are being trained on the system, attempting to resolve once and for all whether this potentially habitable world actually exists. The James Webb Space Telescope might finally have the sensitivity needed to detect atmospheric signatures that could confirm or refute the planet's presence. The story of Gliese 581g represents something profound about humanity's search for other worlds. It shows our deep desire to find planets like Earth, even when the evidence is ambiguous. We want so desperately to believe that habitable worlds exist nearby that we sometimes see them in data that might not support their existence. Whether real or phantom, Gliese 581g has become a symbol of both the promise and the limitations of current exoplanet science. It reminds us that the universe is full of worlds waiting to be discovered, but also that confirming their existence requires extraordinary patience and precision. Chapter 9. Kelt 9b, the planet hotter than most stars. In the cosmic hierarchy of extreme temperatures, stars have always occupied the top tier, while planets remained relatively cool by comparison. Kelt 9b has shattered this fundamental assumption, achieving surface temperatures that exceed those of many stellar objects and creating atmospheric conditions so extreme they're rewriting our understanding of what it means to be a planet. Located 670 light-years from Earth, Kelt 9b orbits a blue-white star that's nearly twice as massive and 3 times as hot as our Sun. The planet completes one revolution in just 1.5 days, locked in such a tight orbital embrace that its dayside reaches temperatures of 7,800 degrees Fahrenheit, hot enough to melt tungsten and approaching the surface temperature of our Sun. To put this in perspective, Kelt 9b is significantly hotter than many M-type red dwarf stars, which constitute roughly 75% of all stars in our galaxy. This gas giant has achieved the extraordinary distinction of being a planet that's literally hotter than the majority of stellar objects in the universe. At these temperatures, the very concept of molecular chemistry breaks down completely. Hydrogen molecules, the most abundant compounds in the planet's atmosphere, are torn apart into individual atoms by the intense thermal energy. Only on the relatively cooler night side, where temperatures drop to a merely scorching 3,000 degrees Fahrenheit, can these atoms recombine into molecular hydrogen. Dr. Scott Goudy from Ohio State University, who led the discovery team, describes Kelt 9b as a planet where chemistry as we know it simply cannot exist. The extreme temperatures create conditions where atmospheric composition changes dramatically depending on location, with molecular dissociation and recombination occurring in real time as atmospheric gases circulate between the day and night sides. But the truly mind-bending aspect of Kelt 9b lies in its thermosphere, the uppermost layer of its atmosphere. Computer models predict that temperatures in this region could exceed 18,000 degrees Fahrenheit, driven by ionization of heavy metal atoms like iron and magnesium. These temperatures are hot enough to ionize virtually any known element, creating a plasma environment that shares more in common with stellar coronas than planetary atmospheres. The planet's extreme proximity to its host star subjects it to radiation bombardment so intense that it's rapidly losing its atmospheric mass. Scientists estimate that Kelt 9b sheds approximately 18 to 68 Earth masses worth of material every billion years, creating a comet-like tail of escaping gas that streams away into interstellar space. This mass loss process is so violent that it's visible from enormous distances using ultraviolet telescopes. The escaping atmospheric material glows brightly as it's heated and ionized by stellar radiation, creating a luminous signature that extends far beyond the planet's physical boundaries. Yet despite this ongoing atmospheric erosion, Kelt 9b appears to maintain a stable atmospheric envelope. This suggests that the planet's interior is continuously replenishing its atmosphere through volcanic outgassing or other geological processes, creating a dynamic equilibrium between atmospheric loss and renewal. Recent spectroscopic observations have revealed another extraordinary feature of Kelt 9b's atmosphere. The extreme temperatures have created conditions where normally stable compounds undergo continuous chemical transformation. Iron exists simultaneously in multiple ionization states, while exotic molecules that don't exist under normal planetary conditions form and dissociate in rapid cycles. The planet's magnetic field, generated by its molten interior and rapid rotation, creates additional complexity in its atmospheric dynamics. Charged particles trapped in magnetic field lines generate auroral displays that would dwarf anything seen on Earth, covering vast regions of the planet in sheets of plasma emission, visible across multiple wavelengths of light. Kelt 9b represents the extreme limit of what we can still classify as a planet rather than a failed star. Its interior temperatures and pressures approach those found in the cores of low-mass stars, yet it lacks sufficient mass to initiate nuclear fusion. It exists in a twilight zone between planetary and stellar physics, challenging our fundamental definitions of these cosmic categories. The discovery of Kelt 9b has forced astronomers to expand their models of planetary formation and evolution to include conditions previously thought impossible. It's shown that planets can exist in environments so extreme they blur the boundaries between different types of celestial objects, opening up entirely new categories of worlds for future exploration. Computer simulations suggest that Kelt 9b's extreme heating might drive atmospheric dynamics that create large-scale circulation patterns unlike anything seen on cooler planets. The massive temperature gradients between day and night sides could generate wind systems moving at velocities that approach hypersonic speeds. The planet's rapid orbital motion and extreme tidal heating also create conditions where its shape becomes significantly distorted from spherical. The gravitational forces from its nearby star stretch Kelt 9b into an elongated form, creating additional stress patterns that could drive geological activity in its interior. Recent theoretical work suggests that planets as hot as Kelt 9b might be more common than initially thought, particularly around massive hot stars. If confirmed, this would mean that the galaxy contains numerous worlds where temperatures exceed those of many stellar objects, fundamentally altering our understanding of planetary demographics throughout the cosmos. Chapter 10. TOI 849b, the naked core that should have been a giant. Deep in the constellation Sculptor, 630 light-years from Earth, orbits a world that represents one of the most profound mysteries in planetary science. TOI 849. B is a planet that shouldn't exist, yet there it sits, mocking our theories of planetary formation with its impossible properties. This world is roughly the size of Neptune, but possesses a density that defies explanation. Instead of being a puffy gas giant like we'd expect from its dimensions, TOI 849b is a solid rocky world 40 times more massive than Earth. It's the largest terrestrial planet ever discovered, yet it orbits so close to its star that a complete year lasts just 18 hours. Dr. David Armstrong, from the University of Warwick, who led the discovery team, describes TOI 849b as a cosmic crime scene where we're trying to piece together what happened to create something so fundamentally wrong. The planet exists in what astronomers call the Neptunian Desert, a region around stars where planets of this size simply don't survive. Here's what makes TOI 849b absolutely terrifying from a planetary perspective. Scientists believe we're looking at the exposed core of what was once a massive gas giant, possibly larger than Jupiter. Something catastrophic happened to this world, stripping away its entire atmospheric envelope and leaving behind only the dense, rocky heart that we observe today. The temperatures on TOI 849b's surface reach 2800 degrees Fahrenheit, hot enough to melt lead and copper. At this proximity to its star, any remaining atmosphere should have been blown away by stellar winds long ago, yet somehow this naked planetary core continues to orbit in stable formation, a testament to the violent processes that created it. Computer models suggest several possible scenarios for how TOI 849b lost its atmospheric envelope. It might have been stripped away by intense stellar radiation over billions of years. Alternatively, the planet could have experienced a catastrophic collision with another world, similar to the impact that created Earth's moon, but far more destructive. Another possibility is that TOI 849b formed through a process called photoevaporation, where high-energy radiation from its host star heated the planet's atmosphere to such extreme temperatures that gas molecules achieved escape velocity and fled into interstellar space. This process would have taken millions of years, gradually peeling away layer after layer of atmospheric material. Recent analysis of the planet's composition has revealed trace amounts of volatile compounds that shouldn't exist at such high temperatures. This suggests that TOI 849b might still possess a thin atmosphere, continuously replenished by outgassing from its molten interior. The planet could be locked in an eternal struggle between atmospheric loss and renewal. The discovery of TOI 849b has profound implications for our understanding of planetary evolution. It suggests that the transition between rocky planets and gas giants isn't as clear-cut as we once believed. Worlds can migrate between these categories through violent processes that reshape their fundamental nature. If TOI 849b truly represents an exposed planetary core, it provides a unique opportunity to study the interior composition of giant planets. The materials we're observing on its surface were once buried beneath thousands of miles of atmospheric gases, hidden from direct observation. The planet's extreme density also suggests that it contains unusually high concentrations of heavy elements like iron and nickel. This could indicate that it formed in a region of its solar system particularly rich in metallic materials, or that its core composition was altered by the violent processes that stripped away its atmosphere. Computer simulations attempting to reproduce TOI 849b's formation consistently struggle to explain how such a massive rocky world could exist in its current orbital configuration. The planet appears to require formation mechanisms that operate under conditions significantly different from those that created the worlds in our solar system. The ongoing study of TOI 849b is revealing that planetary evolution can follow pathways that are far more dramatic and violent than traditional theories suggested. Worlds can experience complete atmospheric loss, catastrophic collisions, and radical compositional changes that transform their fundamental character. Recent observations have detected subtle variations in TOI 849b's thermal emission that could indicate geological activity on its surface. The extreme tidal heating from its nearby star might be driving volcanic processes that continuously reshape the planet's surface composition. The planet's magnetic field, if it possesses one, would be generated entirely by its molten iron core without any contribution from atmospheric dynamics. This could create unique magnetospheric configurations that have no analogues among the planets in our solar system. Theoretical models suggest that TOI 849b's surface might be covered by oceans of molten rock and metal, creating a geological environment where traditional concepts of crustal formation and tectonic activity become meaningless. The planet exists in a state of perpetual geological chaos driven by extreme stellar heating. The discovery has also raised questions about how common exposed planetary cores might be throughout the galaxy. If violent atmospheric stripping is a regular feature of planetary evolution around close-in orbits, there might be numerous naked cores like TOI 849b scattered throughout our local region of space. As we continue studying this impossible world, we're learning that planetary formation and evolution can follow pathways that are far more complex and violent than anything we see in our own solar system. TOI 849b exists as living proof that the universe specializes in creating worlds that challenge our most basic assumptions about how planets should behave. As we reach the end of our journey through the most impossible worlds ever discovered, I want you to take a moment to truly comprehend what we've witnessed together tonight. We've traveled from planets where glass shards slice through alien atmospheres at hypersonic speeds to diamond worlds worth more than entire civilizations. We've watched ancient planets older than time itself dance around stellar corpses and witnessed worlds being slowly devoured alive by their own stars. Each planet we've explored represents a fundamental violation of what we believed possible in our universe. HD 1897-33. B shouldn't be able to maintain its glass rainstorms under such extreme conditions. 55 Cancri shouldn't be able to regenerate its atmosphere after complete stellar stripping. Kelt 9. B shouldn't exist as a planet hotter than most stars, yet here they are, spinning through space in magnificent defiance of our theoretical frameworks. But here's what should absolutely terrify you as you process everything we've discovered tonight. These 10 impossible worlds represent less than 0.0001% of the planets that exist in our galaxy alone. We've examined fewer than 10,000 worlds in any detail out of an estimated trillion planets in the Milky Way. That means 99.999% of the cosmic menagerie remains completely unknown to us, each world potentially harboring phenomena that could revolutionize our understanding of reality itself. Think about the mathematical implications of what this means. If our tiny sample of nearby space has revealed planets this bizarre, this impossible, this utterly alien to our experience, what nightmarish creations are lurking in the unexplored depths of our galaxy? What worlds exist that are so strange we don't even have the scientific vocabulary to describe their properties? The universe has shown us planets where iron rains from metallic clouds, where entire worlds exist as wandering orphans in eternal darkness, where atmospheric chemistry operates according to principles that shouldn't exist. And these represent the tame discoveries, the worlds we've been able to detect and study with our current primitive technology. As our telescopes become more powerful and our detection methods more sophisticated, we're going to discover worlds that make tonight's impossible planets seem mundane by comparison. We're going to find atmospheric compositions that violate the laws of chemistry, orbital mechanics that defy gravitational theory, and planetary structures that challenge our most basic understanding of how matter behaves under extreme conditions. Dr. Sarah Seeger from MIT recently admitted that every new exoplanet discovery forces astronomers to throw away another piece of conventional wisdom about planetary science. We're not just finding strange worlds scattered randomly through space. We're uncovering systematic evidence that our universe operates according to principles so alien to our experience that they challenge the very foundations of planetary physics. But perhaps the most disturbing realization from tonight's journey is what these discoveries reveal about our own cosmic situation. Our solar system, with its orderly arrangement of planets following predictable orbits and exhibiting reasonable physical properties, might be the cosmic exception rather than the rule. We might be living in one of the universe's rare islands of planetary normalcy, surrounded by a galaxy filled with worlds so bizarre they operate according to physics we don't yet understand. Every stable orbit, every temperate climate, every predictable seasonal cycle we experience on Earth might represent winning tickets in a cosmic lottery where the overwhelming majority of planets face conditions so extreme they defy imagination. The gentle blue skies above your head tonight exist in stark contrast to the glass rain hells and molten lava worlds that populate the darkness between stars. Yet these impossible worlds also represent something profoundly beautiful about the universe we inhabit. They demonstrate that cosmic creativity operates on scales that dwarf human imagination, that the fundamental forces of nature can combine in ways that produce phenomena more spectacular than any science fiction writer has ever conceived. Each impossible planet we've discovered tonight exists as a testament to the universe's infinite capacity for surprise, for creating beauty and horror on scales that challenge our ability to comprehend. They remind us that in a cosmos spanning billions of light years and operating according to principles that consistently exceed our theoretical frameworks, the boundaries between the possible and impossible become meaningless human constructs. The story of planetary discovery is just beginning. The James Webb Space Telescope is revealing atmospheric compositions on distant worlds with unprecedented precision. Future space missions will detect biosignatures in alien atmospheres, potentially revealing that life itself has learned to adapt to conditions we consider impossible. We might discover that consciousness has evolved on worlds where diamond cores generate magnetic fields strong enough to contain plasma atmospheres, where organisms thrive in the molten iron rain of tidally locked worlds. As you look up at the stars scattered across the darkness tonight, remember that you're not gazing into an empty sky filled with familiar, Earth-like worlds. You're witnessing a galaxy populated by planets so strange that discovering them has forced humanity to confront the uncomfortable truth that we understand almost nothing about the cosmic environment surrounding our small temporary island of stability. Behind each point of light lurk worlds where the very concepts of solid ground, stable weather, and predictable chemistry become meaningless. Planets where atmospheric pressure can compress water into forms of matter that don't exist in our terrestrial experience. Worlds where magnetic fields generated by exotic planetary cores create auroral displays that would dwarf anything seen on Earth. The universe has revealed its capacity for creating the unimaginable, and we've only begun to catalogue the infinite variety of its planetary nightmares and wonders. In the vast darkness between stars, impossible worlds continue their ancient journeys through space, each one spinning in magnificent defiance of everything we thought we knew about the fundamental laws governing planetary existence. These discoveries represent more than just exotic curiosities for astronomical textbooks. They're evidence that we inhabit a cosmos far stranger, far more violent, and far more creative than we ever dared imagine. Every impossible world we've uncovered tonight exists as proof that the universe operates according to rules that extend far beyond the comfortable boundaries of human theoretical understanding. So tonight, as you rest and your consciousness gradually dissolves into sleep, carry with you the knowledge that somewhere in the darkness beyond our atmosphere, worlds of diamond and glass and molten metal continue their eternal dance around distant suns. They spin through space in defiance of our expectations, each one a monument to the universe's infinite creativity and our own profound limitations in comprehending the true scope of cosmic possibility. The impossible has become inevitable in a universe that creates what it chooses to create, regardless of whether our physics can explain how or why such creations should exist. And in the silence between heartbeats, between one breath and the next, new impossible worlds are being born in stellar nurseries scattered throughout our galaxy, each one destined to challenge another fundamental assumption about the nature of planetary existence. The cosmic catalogue of impossible planets continues to grow, and the universe patiently waits to surprise us once again with its capacity for creating worlds that shouldn't exist, yet spin majestically through the infinite darkness as permanent reminders that reality is far stranger than we ever dared imagine.